This lecture is about an introduction to number theory. And we're talking about multiples and divisors. So first, let's say when we study number theories, we're concerned ourselves with positive integers. Positive integers mean 1, 2, 3, 4, these numbers. Some people call them the natural numbers. In contrast with positive integers, there are negative integers, -1, -2, -3. And you will see that in terms of multiple and divisors, the sign does not really matter. The other thing I want to point out is even though we're talking about just integers, you will see that even for decimal points, some problems actually really care about the properties of the integers. Like, if you have $1.21 and let's say each pencil is 11 cents, how many pencils you're going to buy? And the answer is 1.21 divided by 0.11 equals 11. So even though the numbers are decimal points, but actual operation involved is really integer. If you can convert everything into cents, then of course it's 121 cents and 11 cents. Okay, with those kind of limitations defined, we're going to concern ourselves only with positive integers. And multiple and divisors are really about relationship between two numbers. We say a number n and a number k. We say n is a multiple of k if n equals k times something, k times another positive integer a. And that's really the definition of multiples. In that case, we also say k is a divisor of n. Sometimes people call a divisor a factor. K is a factor of n. All right, so definitions are pretty straightforward. And we certainly have a lot of experience with multiples. For example, when we say some number is an even number, what's an even number? An even number if the number is a multiple of 2, right? And we know that multiple of 3, multiple of 4s. And we learn by multiples by start with counting. So for example, the multiples of 4s are 4, 8, 12, 16, and so on. And of course that we learn as 4 times 1, 4 times 2, 4 times 3, 4 times 4. So that's the definition of the multiples. And in that case, we also say 4 is a factor of 12, or 4 is a divisor of 12. Okay? And we also know that just from this definition, to verify n is a multiple of k, if and only if, when I take n and divide by k, and when we do the division, we know that there's a quotient and then there's a remainder if you're only concerned about division in multiples, in integers. Then it's a multiple k if only if that the remainder is 0. Correct? We all know this. right? So let's just look at a few simple examples to remind ourselves how those simple things actually work. Let's look at problem number 1. Is 972 a multiple of 3? All right, and this is of course a very simple problem, but again, I want to stress that how you are going to take those lessons. You look at a problem and you always try it yourself. For this problem, of course, it's extremely simple, and I'm sure some of you already know the trick of checking a number a multiple of 3 or not. But let's first using the definition of a multiple. A multiple of 3 if and only if when I divide it, the remainder should be 0. And if let's divide it, it should be 3, 2, 4, and the remainder 0. Okay, so it is a multiple of 3. Let's look at problem number 2. What is the greatest 3-digit numbers that is a multiple of 7? Okay, for this problem, how we should think. So the first thought should be, what is the greatest 3-digit number? And that is clearly is 999. And you want to check if 999 is a multiple of 7. And the fact is, it's not. If you divide it, it's 1, 4, 2, remainder 5. All right, so you know that this is not a multiple of 7. So what's the next number that is a multiple of 7? Well, the answer is already in your remainder. The remainder of 5 means that if I remove that 5, that number is going to be a multiple of 7. So the answer is 999 minus 5, 994 is a multiple of 7, right? Now, problem number 3, I put it there because I want you to think about some interesting property of these multiples. Problem number 3. Both 147 and 357 are multiple of 7. And that easily you can verify. The question is 147 plus 357 a multiple of 7? Well, in here, you really should think about the definition of a multiple of 7. A multiple of 7 means that it's 7 times something, right? So the fact this 147 is a multiple of 7 means it's 7 times something. In fact, here is 21, right? And 357 is a multiple of 7. And 357 can be written as 7 times 51. The fact what those two numbers are is not really important. The important thing is 147 can be represented as 7 times something, integer, and 357 is also 7 times something. By the definition of, they are both multiple of 7. So now if you add them up, remember, that we have the distributive law. This equals 7 times 21 plus 51. The actual answer, I don't really care. The only fact is, it is again a 7 times something. So of course, by the definition, this number is a multiple of 7. Okay? Similarly, let's think about problem number, no, actually we're talking about problem number 4. So for problem number 3, we can just skip it and you can work on it. So this is problem A of problem 4. Problem B of problem 4 is, I know that 357 is a multiple of 7. So 356 is not a multiple of 7. Right? But why? Think for a second. Why? Why you say that, oh, 357 is a multiple of 7 and 356 is 357 minus 1? The smaller multiple of 7 below 357 should be 350, right? So this cannot be a multiple of 7. All right, good. Now, how about 147 plus 356? Is this a multiple of 7? Think. Well, you actually should say no, because this is a multiple of 7. By definition, this can be written as 7 times something. But this, you cannot written as 7 times something. This is going to be 7 times something plus a remainder. So the whole thing, it will be written as 7 times something plus that remainder. That remainder never can be cancelled out with anything here because this guy does not have any remainder. So this is not a multiple of 7. Okay, so with that, we have a simple rule that we observed. And it's actually fairly easy to verify. But let's just put it down. If n is a multiple of k, then n plus m is a multiple of k if and only if, I put if and only if as if m is also a multiple of k. In problem 4, we basically have is n is, we use 147, k is 7. So 147 is a multiple of 7. Then 147 plus m is a multiple of 7 if and only if m is also a multiple of 7. Right? And a proof of this is actually just think from first principle. If n is a multiple of k, that means n can be written as k times something. A is an integer. And if n plus m also equals k times another integer, that's the definition of n plus m is a multiple of k, then m is going to equal k b, actually let's just using n plus m minus n, this equals kb times minus ka equals, using distributive law, equals k b minus a. All right, this actually uses a bit of algebra, so let me go on this again. M, we want to find out if m is a multiple of k. M can be written as n plus m minus n. And why we break into n plus m minus n? Because n plus m, we know that it's a multiple of k. So we can plug into kb. And n is, we already know, is ka. right? So we plug in kb minus ka, and using distributive law, k times b minus a is a multiple of k. So if n plus m is a multiple of k, then m has to be a multiple of k. Conversely, if n plus m is not a multiple of k, so n plus m divided by k will have a remainder, then m will also have a remainder. Okay? And this is a very important property. And we're going to use this to verify a few known facts that you already have learned, but you probably don't know exactly why. And we're going to understand why. All right. Those properties or the known facts are what makes a number a multiple of something. And let's review them. All right? So review. 1. What makes a number a multiple of 2? You say even numbers, right? Well, that's correct, but not too accurate. The right way of saying it is actually as long as the unit digit is 0, 2, 4, 6, 8. As long as the unit digit is an even number, then it is that number is a multiple of 2. Great. 2. I'm going to group these similar properties together. What makes a number multiple of 5? Well, it's as long as the unit digit is 0 and 5. What does that mean actually for property 1 and 2? It actually says as long as the unit digit is a multiple of 2, then the number is a multiple of 2. As long as the unit digit is a multiple of 5, that number is a multiple of 5. This actually a condition is if and only if. All right? If the number is a multiple of 5, then the unit digit has to be a multiple of 5. And if the unit digit is a multiple of 5, then the original number is a multiple of 5. And let's look at, instead of 2, let's think about 4, a multiple of 4. And the way we're using unit digit, this thing is extendable. A number is a multiple of 4 if and only if the last 2 digits is a multiple of 4. Okay, for example, 124. Is this a multiple of 4? The last 2 digits are 24. And you know 24 is a multiple of 4, so this number is a multiple of 4. Is 2, 3, 3, 1, 8 a multiple of 4? This looks like even number. And if you're going to divide by 4, this number, it's going to be, takes a bit of time. But if you know this property, you only check the last 2 digits. Is 18 a multiple of 4? No, so this number is not a multiple of 4. This has a very similar property as multiple of 4 is the property of multiple of 25. If and only if a number is a multiple of 25, if and only if the last 2 digits is a multiple of 25. So you see that the 4 and the 25 is actually kind of twin brothers. They have exactly the same property. So for example, is 245 a multiple of 25? No, because 45 is not a multiple of 25. Is 675 a multiple of 25? Yes, because 75 is a multiple of 25. Okay? And from this, you can actually guess what makes a number of multiple 8? And a multiple of 125. Careful students probably already observed that 4 is 2 to the power 2, 25 is 5 to the power 2, and 8 is 2 to the power 3, and 125 is 5 to the power 3. So if you notice a pattern, 2, 5, and this is equal 2 to the 2, this is 5 to the 2. For 2, you only need to check the last digit of a number, and 5, check the last digit. For 4, which is 2 to the square, you check the last 2 digits. 25, you check the last 2 digits. And for 2 to the power 3, you're going to check the last 3 digits. Similarly, for 125, also you're going to check the last 3 digits. So now, can you make a guess about what makes a number a multiple of, let's say, 2 to the 5, which is, of course, 32? What's your guess? All right. Of course, you can send the guess to us and to see if you get it right. And that's usually how mathematicians propose conjectures. They see a pattern and they think about, and if they cannot prove, they will propose as a conjecture to challenge the field. And often mathematicians can find a way to prove it, and that becomes a theorem. All right, so these are the properties of making a number multiple of 2, 5, 2 square, 5 square. Let's look at another group. What makes a number multiple of 3? Remember that, the first problem, 972. A number is a multiple of 3 if and only if the sum of the digits is a multiple of 3. So for example, problem number 1, 972. Instead of actually dividing this number by 3 and look at the remainder, you are going to just check, is 9 plus 7 plus 2, which is the sum of all the digits, which is equals 18. Is this number a multiple of 3? And 18 is a multiple of 3 is obvious. So this is a multiple of 3, which means 972 is a multiple of 3 as well. And we're going to actually see why. The property of this is actually very similar to multiple of 9. And we're going to prove that instead of multiple of 3 because the proof is exactly the same. And for multiple of 9, a number is a multiple of 9 if and only if the sum of the digits is exactly the same words. Is a multiple of 9. So let's 972 again. It is a multiple of 9. Well, the sum of digits is 9 plus 7 plus 2 equals 18, which is a multiple of 9. So the 972 is a multiple of 9. And how about 903? The sum of digits is 9 plus 3 equal 12, so which is not a multiple of 9, so this thing is not multiple of 9. And we're going to prove this. All right, so let's go over this proof. And it only uses the property that if n is a multiple of k, only uses this property. If n is a multiple of k, then n plus m is a multiple if and only if m is a multiple. Okay, so let's actually take the example of 972, okay? I'm going to show 972 is a multiple of 9. Is equivalent to 9 plus 7 plus 2 is a multiple of 9. And you will see that what I'm going to show is going to be universal. And this is like any way you're going to using this, any digits there, you're going to use the same method to prove the same thing. And let's look at 972. What this number really mean? It's, of course, it's 900 plus 70 plus 2. And this is 9 times 100 plus 710 times 10 and plus 2, right? Now this equals 9 times 100 equals 99 plus 1 plus 7 times 9 plus 1 and plus 2. Why I'm writing this way? I'm going to be using this property. If n is a multiple of k, n plus m is a multiple of k, if and only if m is a multiple of k. So here, I'm not writing 972 as 9 times 99 plus 1 plus 7 times 9 plus 1 and plus 2. So is this number a multiple of 9? Actually, let's just, using the distributive law to multiply them out, okay? So this is equal 9 times 99 plus 9 plus 7 times 9 plus 7 plus 2. Now I'm going to group those multiple 9 together, which I don't care really like what they are, the numbers are, but as long as I know this is a multiple of 9. So we know this is a multiple of 9. Now the fact is, using that property, 972 is a multiple of 9 if and only if this part is a multiple of 9. Because this part is a multiple of 9 already. So this does not contribute anything in terms of multiple of 9 or not. Only this matters. And they're equivalent. Okay? So if you're having a bit of difficulty understand this, you can rewind and going through this. The important property is if n is a multiple of k, then n plus m is a multiple of k if and only if m is a multiple of k. That basically go through most of the properties except one more. What makes a number multiple 11? Now, this is a little bit tricky to say. And this involves digits on odd positions and even positions. Let's first look at what does the property say. The property says if a number is a multiple of 11 if and only if the difference between the sum of all digits, odd position digits, and the sum of all even position digits is a multiple of 11. What do we mean the odd position digits and the even position digits? Okay, let's look at a concrete example. number, let's say 2, 3, 4, 5, 3. Okay? The outer position digits are positioned at 1 and 3 and 4, the position at 3 and the position at 5. Right? If you count from the right, this is position 1, 3, and 5. The even positions are the remaining positions, the position at 2 and 4. Okay, so we are taking two sums, the sum of all the odd position digits, which means 3 plus 4 plus 2. Let's call it the sum odd. And sum even is the 5 plus 3. So the above, that sum equals 9, this sum equals 8. And the property asks you to take that difference. So SO minus SE equals 9 minus 8 equals 1. And if this is not a multiple 11, then the original, this number is not a multiple 11. Let's look at a number that we know that it's a multiple 11, okay? How about 22? Well, the odd position sum is 2, the even position sum is 2, so 2 minus 2 equals 0. And 0, of course, is a multiple of 11. 0 is actually a multiple of everything except 0 itself. So this is a multiple of 11, so it means 2 is a multiple of 11. Well, you see that, of course, it's too simple that you don't really care. How about let's using a slightly more complicated example, 2772. Is this a multiple 11? Well, if you're using this property, 2 plus 7 is 9, 7 plus 2 is also 9, so the difference SO minus SE is 9 minus 9 is 0. Yes, this is a multiple 11, so that original number is a multiple 11. Let's try another example. 3, 6, 3. Now the odd positions is 3 plus 3. The even position is just 6. Right? So the difference 3 plus 6, 3 minus 6 equals 0. And it's a multiple 11. And this original number is a multiple 11. How we prove this property? It actually follows very similarly as we proving a number is a multiple of 9 if and only if the sum of the digits are multiple of 9. And you can try to work out by yourself. Now, the next discussion is more about looking at a few real properties of those multiples. Okay? And this actually involves a little bit of review. The problem goes problem number 5. Suppose n is a multiple of 13. The actual 13 here does not really matter, and there's really no property of checking a number as a multiple of 13 or not, as far as I know. Here, the fact is 13, I can replace by any number. But if n is a multiple of 13, is it possible n plus 2 is also a multiple of 13? Is it possible? Is it possible you can find such n, such that n is a multiple of 13 and n plus 2 is also a multiple of 13? Think for a few seconds, maybe a half a minute. And the answer is no, not really. Because if n is a multiple of 13, you think about it. You count n to be a 13 times, let's say, a, right? What is the next multiple of 13? The next one, so you know how to count those multiple 13s, right? It's 13 times, let's say, 101. The next one, of course, is 13 times 102, right? I'm just giving an example. for this, in general, n equals 13 times a, the next multiple of 13 is 13 times a plus 1, or equals 13 times a plus 13, using distributive law. And this is equals n plus 13. So you know that if I found a multiple of 13, n, the next multiple of 13 is going to be, you have to jump 13 away. Let's say this is n, is a multiple of 13. The next one is n plus 13. And of course, the next one, again, is n plus 13 plus 13 plus 26. And again, anywhere in between, there's no multiple 13s. No multiple 13s. And no multiple 13s. It's a fairly obvious fact, but sometimes it's easy to forget. And this is a very, very important property. Okay, so let's look at problem number 6. Just to reinforce what you have learned. Is 11 times 12 times 13 times 14 plus 10 a multiple of 13? Okay, think about it. And if you already have finished your thinking, the answer is again no, because this number is a multiple of 13. And remember, if this number is a multiple of 13, the next multiple of 13 has to be plus 13. This number plus 13. A plus 10? No, it cannot be a multiple of 13. So following this, actually I can write down another problem. Is 30 factorial plus 10 a multiple of 13? And by the way, 13 factorial equals defined as 1 times 2 times 3 times all the way to 30. You multiply all the numbers, all the positive integers from 1 to all the way to 30, multiply them together. It's a multiple. It's defined as 30 factorial. It's called factorial, and you write down as an exclamation mark. Is 30 factorial plus 10 a multiple of 13? Again, no. Exactly for the same reason. This number, because when you multiply everything, including a 13 there, so 30 factorial is a multiple of 13. And so a multiple of 13 plus 10, well, the next number, because it's a multiple, the next multiple is, you have to jump 13. Somewhere there, plus 13 is a multiple. Plus 10, no, it cannot be a prime number, a multiple of 13. All right. Got that? Okay. So the other problems will be a review of the properties of what make number a multiple of 2, 3, 4, 5, 8, 9, and 11. All right. So we're going to pick a few problems. Let's pick problem 8. Yes, problem 8. Find the largest x such that 4-digit number (8x54) is divisible by 3. Okay, for this problem, you know that the property of a number that is divisible by 3 is the sum is going to divide by 3. So which means that 8 plus x plus 5 plus 4 is divisible by 3. Okay, we actually can, using this form, 3 is a factor. 3 is a divisor of this number. Okay, and so 3 is a divisor of, if you add them up, equals 17 plus x. Right? And 17 plus x, and you know that if this is a multiple of 3, you can take out all the multiples of 3 there, equals 2 plus x, because 15 is a multiple of 3, right? So this equals 15 plus 2 plus x. And using that property, if this is a multiple of 3 already, and the fact that this whole thing is a multiple of 3 if and only if 2 plus x is a multiple of 3. And so this is a multiple of 3, so which means that x, it cannot be 9, because 9 plus 2 is not a multiple of 3, but 7 is. So the largest value is 7. Okay, so we're going to stop here. Even though on this handout, we still have greatest common factors of 2 numbers and the Euclidean method of doing so. And we're going to do that in the next lecture. All right.